So let us continue discussing congruences. In Z, the integers, and Z mod M, the congruence class is mod M, we have two binary operations, addition and multiplication. So addition in both cases satisfies the following properties. It's associative. There exists an identity element. Every element has an inverse, and addition is commutative. So therefore, Z and Z mod MZ are both additive abelian groups. Multiplication satisfies, first of all, associativity. X, Y, Z equals X times Y, Z. There exists a multiplicative identity. 1 times X equals X times 1 equals X for all X. We have the distributive laws. X times Y plus Z is XY plus XZ. And multiplication is commutative. XY equals YX for all X and Y. So therefore, Z and Z mod MZ are examples of commutative rings. And these are fundamental objects in algebra. We have groups which have one binary operation, addition or multiplication, and we have rings which have addition and multiplication. And with respect to an addition, you have an additive abelian group structure, not with respect to multiplication, but multiplication does satisfy these additional properties. There's one more algebraic structure I need to introduce, and that's something called the field. And before I do that, I need to prove something about congruences. So just the way we solve equations in the integers, for example, 7x equals 56, and the solution is x equals 8, or 7x equals 57, and there's no solution. We can also try to solve equations in Z mod MZ. That is, you might say, can we find a number x such that, so solving equations in Z mod Z, or solve congruences. Mod M. So let me just indicate how these are similar. You could have an equation, solve an equation like let's see, what's a nice example. 5x congruent to 4 mod 6. What would a solution of that congruence be? Well, any integer which is congruent to 2 mod 6, because if x is congruent to 2 mod 6, then 5x is 5 times 2 is 10, and 10 is congruent to 4 mod 6. So for this equation, you get this solution. We could write this as also an equation in z mod z. Can we find a congruence class x such that 5 plus 6z times x plus 6z equals 4 plus 6z? So this is an equation in z mod m and z mod 6z. This is the same as saying 5x plus 6z equals 4 plus 6z, which is the same as saying 5x is congruent to 4 mod 6. So there's an equivalence between solving equations in the ring z mod mz and solving congruences. And I think for simplicity, I'm just going to talk about solving congruences. Now, these congruences, these are just like linear equations. They are linear equations. So we can pose the following problem. When does the congruence ax congruent to b mod m have a solution? You might say this really is algebra, because when you start studying algebra, algebra meant solving equations, linear equations, 2 equations and 2 unknowns, quadratic equations. Well, this is just a linear equation, but for congruences. And this linear congruence has a very beautiful solution. So I'll state this as a theorem. The congruence ax congruent to b mod m has a solution if and only if b is congruent to 0 modulo the greatest common divisor of a and m. Remember, this means greatest common divisor. If d is equal to the greatest common divisor of a and m, and b is in fact congruent to 0 mod d, then the linear congruence ax congruent to b mod m has exactly d pairwise incongruent, that means not congruent, solutions. So this is the theorem. It tells us exactly when we can solve a linear congruence. The congruence ax congruent to b mod m has a solution if and only if the greatest common divisor of a and m divides b. And if that's the case, and if the greatest common divisor is D, then the congruence, in fact, has exactly D different solutions, not M. So the proof is not too complicated. So AX congruent to B mod M, this is true if and only if AX minus B is is M times Y for some integer Y, if and only if, just rewriting that equation, B can be written as AX minus MY for some X and Y. And this means that B is a linear combination of A and M. So if and only if B is divisible by the greatest common divisor of A and M. If AX is congruent to B mod M, then you can write B in the form AX minus BY. So this number is divisible by the greatest common divisor of A and M. And conversely, if B is divisible by this greatest common divisor, then it's an integral linear combination of A and M. And rearranging it, you get a solution of this congruence. So that's the whole proof of the first part. And how do we prove that if there is a solution, there are exactly these solutions? So to prove the second part of the theorem, let's look at the special case. Suppose D, which is the greatest common divisor of A and M, is 1. Suppose A and M are relatively prime. We know that, so then D, which is 1, certainly divides B, so a solution exists. Suppose that we have two solutions, that U and V be two solutions of the congruence AX congruent to B mod M. So we have AU is congruent to B mod M, and AV is congruent to B mod M. This implies AU is congruent to AV mod M, which means M divides AU minus AV, which is A times U minus V, which implies M divides U minus V by Euclid's lemma. Euclid's lemma says that if M divides a product of two integers and it's relatively prime to one, it divides the other. So M is relatively prime to A. That's the case we're in. So M divides U minus V. So M divides U minus V means U is congruent to V mod M, which means AX congruent to B mod M has exactly one solution modulo M. So if the greatest common divisor of A and M is 1, the linear congruence has just one solution. So that's a special case of the theorem. The theorem says that if the greatest common divisor of A and M is D, then the congruence has D solutions. So we know this is true when D is equal to 1. So let's look at the general case, D is greater than or equal to 1. So AX congruent to B mod M, and so D is greater than or equal to 1, D is the greatest common divisor of A and M, and D divides B. So if this is the case, this means if for any solution, AX minus B equals M times Y. If you divide by D, A over D times X minus B over D equals M over D times Y. So X is a solution of the congruence, A over dx congruent to B over D mod M over D. And because A and M have greatest common divisor D, A over D and M over D have greatest common divisor 1. So this congruent star has a unique solution. So again, let's just repeat. Suppose D is greater than or equal to 1. D is the greatest common divisor of A and M. If AX is congruent to B mod M, then A over D times X is congruent to B over D mod M over D. And this congruence has a unique solution mod M over D. So suppose we have two solutions, AU congruent to B mod M and AV congruent to B mod M. In that case, we have that A over DU is congruent to B over D mod M and M over D. And A over dV is congruent to B over D mod M over D, which means U is congruent to V mod M over D, which means U is equal to V plus some multiple I M over D mod M, and I can go through the integers 0, 1, 2 up to D minus 1. So we have D choices. These numbers are pairwise incongruent modulo D, and they give all possible solutions. So there exist the congruence has exactly D solutions. Let's look at some examples. Suppose we want to solve the congruence, 3x congruent to 7 modulo 11. So in this case, A is 3, B is 7, M is 11, and D, which is the greatest common divisor of 3 and 11, is 1. So this congruence will have a unique solution. And how do we find it? Well, there are lots of ways to try to find it. You could do trial and error. So suppose we have x, 3x, and what 3x is congruent to mod 11. So if x is 0, 3x is 0, and 0 is 0 mod 11, not 7. If x is 1, this is 3, and this is 3. If x is 2, 3x is 6. If x is 3, 3x is 9, mod 11, that's also 9. When x is 4, 3x is 12. 12 is 1 mod 11. When x is 5, 3x is 15. That's 4 mod 11. When x is 6, 3x is 18. That's 7 mod 11. We win. So solution, one solution is x congruent to 6 modulo 11. This is like the first method. What's another method? Well, if the greatest common divisor in 3 and 11 is 1, this means you can write 1 as a linear combination of 3 and 11. For example, 4 times 3 plus minus 1 times 11 equals 7. Sorry, equals 1. You can get, I just found this, but you can also get this from the Euclidean algorithm. Multiply this equation by 7. 4 times 21 oops, let's see, let me draw this in the right way. Should have written this as 4 times 3. So if I multiply this by 7, 28 times 3 plus minus 7 times 11 is equal to 7. That says that 3 times 28 is congruent to 7 mod 11. 28 is congruent to 6 mod 11. So I can also say that 3 times 6 is congruent to 7 mod 11. So any number x congruent to 6 mod 11 is a solution. Any number. So what are the solutions of the congruence? Six, 17, 28, 39, 50, minus 5, minus 16, minus 27. Anything that satisfies this congruence is a solution. There are infinitely many integers, but exactly one congruence class. Let's look at another example. Instead of 3x congruent to 7 mod 11, suppose we look at 3x congruent to 7 mod 15. So in this case, A is 3, B is 7, M is 15, D, which is the greatest common divisor of A and M, which is the greatest common, oops, I better not have the 7, is the greatest common divisor of 3 and 15, that's 3. 7 is not congruent to 0 mod 3. So this congruence has no solution. This is example 2. No solution. What about example 3? Suppose I want to solve 3x congruent to minus 9 mod 15. In this case, D, which is the greatest common divisor of A and M, is 3. B is minus 9, which is congruent to 0 mod 3. So therefore, there are 3 incongruent solutions modulo 15. So to solve 3x congruent to minus 9 mod 15, if we divide by 3, that's the same as x congruent to minus 3 mod 5, or minus 3 is the same as x congruent to 2 mod 5. Let's just check. 3 times 2 is 6, and 6 minus minus 9 is 15. So x congruent, x equal 2 is certainly the solution. And what are the numbers congruent to 2 mod 5 that are different modulo 15? We have 2. 2 plus 5 is 7, and 7 plus 5 is 12. So we saw that three times 2 is congruent to 9 mod 15. 3 times 7 is 21. It's also congruent to 9 mod 15. 3 times 12, that's 36, is also congruent to minus 9 mod 15. So these are all solutions. That is, those congruence classes give all solutions of the equation. Okay, so this is the theorem about solving linear congruences, and this is something that we will use several times. That's it.